Part 2 of the lab is looking at applications of the impulse momentum theorem. So the impulse momentum theorem is very similar to Newton's second law. And what do I mean by that? When you write, if delta P, which is equal to J, is not equal to 0, even though this is a change in momentum, this also is proportional to acceleration. It's just that we're using a different language to actually talk about it. Now, the power of the impulse momentum theorem is that it allows you to look at things sort of like before and afterwards. Whereas with Newton's laws, you actually have to do a time evolution of the solution. So there's two parts here. So here, the first part that we're going to be looking at is that we're going to measure what people call impact forces. And if we're talking about momentum, we really are talking about two different forces here, right? We're really talking about, are we talking about max versus F average? And it turns out that the average force is difficult to measure. So what we'll do here is that we're really going to, we're going to measure F max and contact time. Otherwise, we have to use the mean value theorem to get the average force. But if we're talking about things conceptually, then that's the way we want to really do that. The second thing that we're going to look at is we're going to measure time. And the way we measure time with the impulse momentum theorem is we essentially say that if we have an impulse that's external to an object, in our case, it's going to be external to a cart, we can use the mean value theorem to say that the average force times the time is then going to be the change in momentum. So what our goal here is essentially, by knowing what the average force is and how are we going to know this average force? Because we're going to try to keep it constant. And then we're going to look at the change in momentum, really proportional to the change in speed of an object. And we're going to ask, how long does it take to speed up a certain object? But that's how we're going to use the impulse momentum theorem in its applications. So let's deal with the first one here. And we're going to talk about, I should probably call this A and call this measuring the so-called impact force. And in this case, F max is much easier than F average and contact time. Which we then define as delta T. So that's the first part of this second half that we're looking at. So let's go look at what we have here. So when we're looking at this, what are we going to do? So this is really a conceptual prediction. So here, we will make a conceptual prediction Why is this a conceptual prediction? Because we don't really have all the numbers to deal with that. We could, but it just turns out that it ends up being difficult. So that's why we're really doing this. So here we're going to make a conceptual prediction on F max and delta T between a superball / clay collision with a force plate. And what the force plate does is it really just measures force and time. That's all it's going to do. So here we go. So the first thing here in part A here is that we want to make a prediction. Okay, so our goal here is that we want to get a prediction. So what's the prediction? We're going to drop a superball / clay ball onto a force plate. Remember what it does. It again measures forces and time and predict the size of F max and delta T for each. And the hint that I'm going to ask you to do here is that my hint here, think about the contact time. Right? We talked about this in lecture. So in this situation, what are we doing here? We have a ball that we're going to drop, and this is a bouncy ball. Let's call that this is the super ball, right? Here's our super ball. And then I'm going to have a glob of clay. And this is going to be our clay. And what we're going to do here is that we're going to drop it from a height of, let's say, 2 meters. So what we know here is down here at the bottom is that we have a force plate. And this thing is going to measure the force and the contact time. And so now what's going to happen to the ball and the clay? Well, it's going to come down here. And the only thing we care about is what happens right before and what happens right afterwards. So what you're seeing here is that right here, we know that the ball is going to get to right here. And this is going to be right before the collision, right? So we know that the speed of this guy is going to be V1. And then we're going to have this clay ball right here. And we know that the speed of this clay right here is also going to be the exact same speed. So now these guys interact with the force plate. By the way, I didn't write this, but I should write it here, that this yellow guy is the force plate. So that's where all the measurements occur right there. So now, what I want you to do here is tell me which one is going to have the maximum force and which one's going to have, the bigger contact time. Okay, so now that you've made your prediction here, now we could move on and actually do that here. So now you have a prediction. So now what we're going to do in parts B and C, what you're going to do here is that you're going to drop. So now you're going to do a little tiny activity where you're going to do the experiment. So here, we now want you to drop. So now actually drop these objects onto the force plate. And so what are you going to actually see here? Well, for starters here, you're going to see that your force versus time curve is not so pretty anymore. So if you look at your force versus time curve, in the beginning, they typically behave nicely, but then they go all crazy afterwards. And part of that, we talked about this in lecture as well, is that part of that, when you're looking at this force versus time curve, is that there's actually oscillations. Like the super ball actually oscillates. The clay even oscillates. So when you're looking at this guy, you're going to have not a nice force versus time curve. So you're going to have to learn how to read these a little bit. So what are we measuring here? The best that you can do is that you can measure F max. That is, what's the peak value? The second thing that you need to measure is that you need to measure the contact time. Okay, there's the contact time. So now let's set up a table to record values. So what we know here is that we have a super ball. And you're going to drop a clay ball. And what we want to measure is we want to measure its max force in newtons, and we want to measure its contact time in seconds. So the contact time might be a little bit tricky here. And we'll talk about the setup here a little bit more. But that's the table that we want you to set up with. So now, you now have results that you could then go and see what your predictions are from the super ball versus the clay. So now let's look at what's going to be tricky about this. One, so use the capstone coordinate tool to measure F max and delta t. Now, delta t might be a little bit tricky here. So what I would do here is that make sure that that force sensor is going on all the time. So keep the force sensor recording all the time. So then you don't have to worry about when are you going to drop the ball or whatever. So once you drop the ball and you see it hit it, then stop it. And when you stop it, then use the delta tool to get delta t. Otherwise, you're going to be subtracting really small numbers. And if I remember correctly, you're going to have to increase your number of sig figs on the timer because it typically only gives you like 2 or 3. So you might have to go to more digits. Otherwise, you're going to get 1 digit. And you shouldn't get too many because, you know, it's still a crude experiment. Okay? So that's how you're going to compare the super ball to the clay ball. The second thing that we're going to do is that now we're going to take, so the lessons learned from parts A through C, we want to apply them to jumping. So what are we going to do here? What we're asking you to do here is that you want to make a reasonable jump from an elevated position. I remember when I introduced this many, many, many years ago. I first did this in Physics 11, and I didn't realize how much people got into this challenge to see who could get the max force. We don't want to get into that type of predicament. Okay, we do not want to get into that predicament. Before I realized, I was wondering if I was going to be calling 911. So here's what we want to do. What we want to replicate here is that you could imagine that you have a table. And what you do here is that you might be standing here at the table. And what you're going to do here is that you're going to jump off the table. And we want to look at two landing possibilities. One here is that the most reasonable thing is that when you land, you actually bend your feet. Now, bend your legs. Ooh, that would be painful to bend your feet. Don't do that. Okay. The other situation is if you jump, that you land and you lock your knees. Here, you lock your knees. Well, as you could imagine, if you lock your knees, Julia is going to be calling 911. But if you bend your knees, you're going to be okay. So the question is, why are you okay? So now what we want to do here is that we want to measure what that means here. So now here, what we're asking you to do is that you're going to jump from a low step stool. Like, please do not jump off the lab benches, which is what happened in that Physics 11 case. And yes, somebody hurt their knee. I wasn't supposed to laugh, but I told them you were a dumbass for doing that. Oh, I'm recording. Maybe I shouldn't have said that. Okay, but here's what we want you to do. You're going to take this low stool, and if I remember correctly, the stool has some steps, and it's pretty low, right? So we have this step stool that you're going to jump off of, and what you're going to do here is that we're going to place this force sensor or this force plate right here. Okay, so again, this is the force plate. So what we're doing here is that we're asking you to take a position that is very comfortable for you, and you want to jump off onto the force plate. So this is very similar to the previous example. So in one situation, we want you to bend your legs. And then this one, we want you to have less bend in your legs. And then we want to measure the max force again, and we want to measure your contact time again. So it's very similar to the clay and the Super Ball. So now your goal is to measure these 4 values. Now, it turns out that the contact time is going to be the hardest to measure. So the contact time is most challenging to measure. Now, the way the force plate reads is that your feet are pushing down on the plate. So you could imagine that so if you have the force plate right here, and you land on it, look what's going to happen here. At first, you land on your feet and you are bending your legs. Okay, you are bending your legs. So you initially land on the plate. And again, your legs are bent. So this is what happens here. So what happens here is that if you look at the force versus time here, that lens shows that there's going to be a spike right there. But the thing that actually happens almost instantly, as soon as you land, you then push down again to have your body go up. And so what you're finding here is that now there is a second peak. Now note, this is smooth. So in order to kind of estimate your contact time, we're asking you to extrapolate the first bump all the way down. So then this is the estimated contact time. That's the tricky piece. So remember that there's two pieces to this. And I have tried numerous times not to do that, but it doesn't work that way. Okay, so fill out that table and go in that direction. So now let's go to the last piece. So now we'll go to part 2. And in part 2, we're going to predict the speed. No, not the speed. We're going to predict the time to speed up a cart. So how do we do this here? We're going to use the application of the impulse momentum theorem because we can treat it like Newton's second law for the large portion of the time. So now we want to apply the impulse momentum theorem. Again. So what you're going to find here is that now, so if I look at the impulse, we know that through the mean value theorem, this is just the time average force times the contact time. And then this is equal to the change in momentum, which will then be, because the mass is fixed in this situation, we're going to have the difference of two speeds here. So as we have done this multiple times now in lecture, this is where we're headed for in this form right here. So what are we going to do here? So what we want to do here is that we want to apply a constant force to a cart starting from rest. Okay, so we're going to apply a constant force to a cart that speeds up to V2 equals to 0.60 meters per second. So if I look at this thing, I'm going to have a cart. So let's say that this is my cart right here. And let's say that in this situation, I have a blue cart. And so when I look at this cart, what I'm going to see here is that I imagine that this cart starts initially at a speed of 0. So now what I'm going to do is that I'm going to take my scale, my spring scale, and I am going to pull on that spring scale. So in this situation, I am then going to apply a force using this spring scale where I now have an average force that I apply that's going to be 0.40 newtons. 0.40 newtons. So then I'm going to continue to speed up this cart for a period of time until this cart reaches a speed of V2 equal to 0.60 meters per second. Right? So that's what we're trying to do right here. So then the question is, how long do you have to apply F average to get V2? Well, that's an example of, the impulse momentum theorem. Okay, so predict this time using the impulse momentum theorem. And you can see it's the one here in the red box right there. So now the question, what is it that we know? Well, first, you're going to need the mass of the cart. So use the weight scale to measure that, the mass scale to do that. You're going to set the spring force to 0.40 newtons, and you're going to have to practice that a little bit. So you're going to have to do a couple of trials to see how well can you keep it to 0.4 newtons. Are you going to keep it at 0.4 newtons the whole time? No. What we want here is that we want that to be the average force. Sometimes you're going to be a little bit over 0.4, sometimes you're going to be less, but the average has to be about 0.4. We know that the initial speed is 0, and we know that the final speed that we want to get is 0.60 meters per second. How do I know when the speed here? So in Capstone, set up position versus time. So we've done this a couple of times, not position, I would say velocity versus time. If it's really jumpy, then you should go to position. But I think with the smart carts, it should be pretty smooth. And what you're going to find here is that you're going to have a curve that looks like this. And you want to plot velocity versus time. And what you're going to find here is that if you move this at a net force that's constant, then you're going to get a curve that looks like this. It's going to be a linear line. So then go onto your scale here and find out at the point where this is 0.60 meters per second, then drop down, and you know here that this is going to be the time required to do that. So this is how you're going to measure the time. Okay, that's how you're going to measure the time. So then when you look at the impulse momentum theorem, you know the force, you know the mass because you measured it. You know all of these guys. The one thing that you don't know is the time. So then set up a table. You have a predicted value. What did you predict? What did you measure? And what you're looking at is you're looking at the contact time required in order to do this. Okay, that should set you up for the lab.